Chapter 3a, Semi-empirical formulation of kinetics in mass transfer limited systems. You have learned about several electroanalytical methods in the previous chapter. In that chapters, you have met several equations about the electroanalytical methods. The Landers-Sevchik equations for current-potential relationship, Cottrell equation for current versus time relation, and the Sand equation is for potential time relation. Those three equations are derived from the reversible reactions. What is the meaning of reversible reactions? Reversible reactions is the reaction which is very facile or fast. That is to say, your mass transfer process is much slower than the charge transfer reaction kinetics. So, the overall kinetics is limited and also controlled by the mass transfer. So we have obtained those three representative equations for electroanalytical methods was based on the mass transfer limited systems. Actually, those equations are the analytical and exact solution of diffusion equations by solving the ordinary differential equation with initial conditions and boundary conditions. Before going for deriving the exact solutions, simpler derivation is presented with the semi-empirical assumption in this chapter. Please refer to the Bard and Faulkner book about 2.1 and 1.4 chapter. I'd like to start with what is the meaning of mass transfer controlled systems and their premises, and then go to Nernst Equation again. Then I will present about the semi-empirical relationship between current and potential, also current and time in this chapter. What is the premises for deriving the equation for mass transfer controlled systems? The first premise for deriving deriving equations for the mass transfer controlled systems is that electrochemical reaction is facile or reversible or Nernstian. Those three words are a kind of trilogy of equality. So when you are saying about reversible reaction, it means your reaction is facile and also your reaction is Nernstian. Nernstian. What is the meaning of Nernstian? You have a very fast and facile electrochemical reactions on the surface of electrode. So the surface composition or surface concentration of oxidized species and reduced species follows the Nernst equation, which is the thermodynamic equation of electrochemistry. So it is the reason why the reversible reaction is called Nernstian reaction, or your reversible reaction is Nernstian. Again, Nernstian means surface concentration is determined by the Nernst equation. So, based on these premises, we have very fast kinetics of charge transfer, which is much faster than the mass transfer kinetics. So we could say the overall system is controlled by mass transfer. Here is the overall process of the electrochemical reactions. Let me symbolize the oxidized species as open circle and reduced species as solid circle. Oxidized species is diffused into the electrode surface and then charge transfer, and then the reduced species is diffused out from the surface to bulk electrolyte. So those step is mass transfer step. The other thing is charge transfer step. So we should think about the competitiveness between charge transfer and mass transfer in terms of kinetics. This is the first situation, which is about the reversible reactions or mass transfer limited system. Here is the electrode, and then also we have electrolyte. I have drawn several molecules of charge carriers in electrolyte schematically. We have 1, 2, 3, 4, 5 layers of electroactive species, and each layer have 8 molecules. Also, I have applied a potential into the system, the value of which is the standard reduction potential. And also, in this situation, at the very first time, I have only oxidized species. Of course, after I have applied the standard reduction potential into the system, some portion of oxidized species is converted to the reduced species. In the bulk region of electrolyte, we have only oxidized species. However, in the surface of electrode, we have the reduced species. Let me check the composition of those electroactive species in terms of reduced species and in terms of oxidized species. We should have the equimolar concentration of oxidized species and reduced species. That is to say, we have 4 oxidized species and we have 4 reduced species, because you have applied the potential at its standard reduction potential. At the standard reduction potential, you should have the same amount of reduced species and oxidized species. So this situation is following the Nernst equation on the surface, because your charge transfer kinetics is much faster than the kinetics of mass transfer. Let me think about the another layer except of the surface layer. Again, in the bulk electrolyte, you should have only oxidized species, because at the very first time before you have applied the potential, you have introduced only the oxidized species. However, from the third layer of the electroactive species molecules, you can find one reduced species, because some reduced species generated on the surface of electrode is diffused out to the electrolyte. And then let's go to the second layer. We have 2 reduced species. If you have only a linear diffusion, maybe on the surface of electrode, you should find 3 molecules of reduced species. However, you have 4, because your surface composition should follow the Nernst equation instead of diffusion equation. So you have 1, 2, and not 3 but 4 on the surface. Let me draw a schematic line of the concentration profile of oxidized species. Fifth layer, fourth layer, and then going down from the third layer with the same slope, we are going to the second layer, and then steeper drop onto the electrode surface. The concentration gradient, or the slope of the concentration profile around the surface, will determine the current of this process. So this steeper slope is proportional to the current. That is the situation of the mass transfer limited system. Let me check several things more. So I could say those three layers is belonging to the diffusion layer, because you can find some concentration gradient. However, about the fourth and fifth layer of the electroactive species, you could say they are belonging to the bulk electrolyte region. Also, I'd like to emphasize again, at the standard reduction potential, the surface composition should be based on equimolar concentration of oxidized species and reduced species. Okay, let's go to the other case. Of course, in this case, your charge transfer is slower than your mass transfer. So, your charge transfer would determine the overall kinetics of electrochemical process. So I have said your mass transfer is really fast. Actually, faster than the charge transfer. So from fifth layer to the second layer, you have only the oxidized species, because mass transfer is really fast. However, on the surface of electrode, you should find some reduced species. Here we have two molecules of reduced species. Let me compare the number of these reduced species with the number of the reduced species in the case of mass transfer limited system. Here is 2 and here is 4. Why should we have less number of reduced species on the charge transfer limited system? If your charge transfer kinetics is fast enough to follow the Nernst equations, then you should have 4. However, the charge transfer, I mean the electron transfer from the electrode to electrolyte, is very slow. So we cannot follow the law of Nernst equation, or we cannot follow or cannot meet the thermodynamic rule. So we have only 2 molecules of reduced species. So again, on the surface of electrode, in this case, the oxidized species is more than the reduced species. The current is determined by the charge transfer kinetics. Also, in this case, you have a thinner diffusion layer when compared with the mass transfer limited system, and you have 4 layers belonging to the bulk region. That is the first premise for deriving equation about the mass transfer controlled systems. Let's go to the second premise. We are saying about the mass transfer, and in this second premise, I'd like to say that diffusion governs the mass transfer, while migration and convection are neglected. This is the mole flux of species I. The unit, let me change my tool. The unit of the mole flux is mole, mole, MOL, per centimeter square second. So that is the mole flux. And mole flux is driven by three different driving forces. The first driving force is concentration gradient. And the process based on the concentration gradient is called diffusion. Actually, you have learned about that. The second driving force is the potential gradient, and the process based on the potential gradient is called migration. The third one is convection, which is based on the velocity of flow. So we have three terms to determine the mole flux. And by using these equations, we will solve the governing equation for obtaining the equation for the mass transfer controlled systems. It sounds complicated because we have three different terms on the right hand side of the equation. So I'd like to kill the migration term and convection term. Then finally we have a simple governing equation. Actually, it is not the governing equation, it is a kind of the definition of mole flux. But anyway, based on this definition, you will have the governing equation. So we have simple mole flux equation. What is that? Mole flux is equal to the diffusion. Well, mole flux is proportional to the concentration gradient. And from this equation, you could obtain the concentration profile. Then I have said we will kill the migration term and convection term. How? By adding supporting electrolyte into the electrolyte having the electroactive species of your interest, then you could kill the migration term of electroactive species. What is the supporting electrolyte? A supporting electrolyte is inactive ionic species. For example, sodium plus and chloride minus in an appropriate potential range, then they have no reaction based on reduction and oxidation, then you could consider those charge carriers or ions as supporting electrolyte. Usually, we have very small amount of electroactive species in electrolyte with a bunch of supporting electrolyte. For example, let me say 0.1 millimole Fe3 plus you have in your electrolyte. And how about a supporting electrolyte like 500 millimolarity of NaCl, millimolarity NaCl, Na plus and Cl minus. Then what happens when you have introduced the supporting electrolyte in your electrolyte? So at the very first time you have only electroactive species like Fe3 plus. You have only 3 Fe3 plus. And then you have applied 60 millivolt to the electrode. Then Each Fe3 plus is responsible for 20 millivolt compensation. The electroactive species, here we have 3, have a burden of 60 millivolt. Those 3 guys should compensate the applied potential at 60 millivolt. Then let's pour a supporting electrolyte. Here is the schematic picture about the case, and totally we have 20 charge carriers, including 3 electroactive species and 17 the supporting electrolyte charge carriers. So in this case, each molecules or charge carrier is responsible for 3 millivolt compensation. That is to say 60 millivolt per 20 charge carriers, so it is going to 3 millivolt. The electroactive species have a burden of just 9 millivolt because we have only 3 charge carriers of electroactive species. So the electroactive species feel much less potential gradient in the presence of the supporting electrolyte when compared with the situation having only electroactive species. Then you could kill the migration term for the electroactive species. Let's go to the convection term. How can we kill the convection? Of course, don't touch your electrolyte. No stirring, no agitation, no shaking. If you have only diffusion, you could have this kind of schematic concentration gradient. From the viewpoint of oxidized species, 5, 4, 3, 2, 1, something like that. However, when you stir your system of electrolyte, then more oxidized species are distributed around the surface. If you have a well-defined laminar flow, then you could expect the concentration gradient by some equations. However, if you are driving some turbulent flow in your electrolyte, then we cannot expect any concentration gradient or something. So we could not solve the problem. So in this case, we'd like to kill the effect of convection. So we are going back to the simplification, which is the mole flux is equal to the diffusion process. Let's go to the last and the third comment about deriving the equation for the mass transfer controlled system. What is the current? Until now, we have said about the mole flux. Then how we can convert the mole flux into current, which is the electrochemical parameter. Simply, current is mass flux. Of course, you have something. But anyway, the current is mole flux, well, mass flux. Specifically at the surface of electrode. That's it. Usually, you could find a group of NFA in any equations for electrochemistry. So, current per NFA is the mole flux of your electroactive species on the surface. So let me check the unit of the current per NFA. What is the current? Okay, let me say about Fe3 plus. You have Fe3 plus as an electroactive species, Fe3 plus. Then the unit of current is, let me change my hand. Unit of current is Coulomb Fe3 plus. Oops. per second. That is the ampere per, what is the N? More. It's very difficult to write down today. More Fe3 plus. No. More electron per more. Let me just write down M. Fe3 plus. Fe3 plus. And then, what is the unit of Faraday constant? That is the charge of mole of electron. Mole of electron. And A is the electrode area, centimeter square. So, let me remove some things. Mole electron, Coulomb, and Coulomb, and that's it. So the final unit is mole Fe3 plus per second per centimeter square. That is the mole flux, right? So I can say the current could be determined by the mole flux, and the mole flux is determined by concentration gradient because we have only diffusion term. So again, current is determined by the concentration gradient. Can you remember? You have learned about the cyclic Voltammogram. At this chapter, I have said about the concentration gradient. So let me say again about that a little bit more. So here is the cyclic Voltammogram, and I'm moving the potential from the positive value to the negative value. Then I follow this point A, and C, and D, and E, and G. So at the point A, we have just applied the potential, and the potential is far beyond or far more positive than the standard reduction potential. So nothing happens. It means we have the oxidized species over the X, or the distance from the electrode. So this kind of concentration gradient is obtained. Then let me check the slope, because the slope is concentration gradient. So slope is 0, concentration gradient is 0, so current is 0. And then let me move more negative potential, and finally we have reached around the standard reduction potential. At the standard reduction potential, you have the equimolar concentration of oxidized species and reduced species. Let me say, at the very first time we have 1 millimolarity of Fe3 plus, but right now 0.5 molarity of Fe3 plus and 0.5 molarity of Fe2 plus. So then we have a slope like that, and slope is larger than the very first time slope, so we have 14 microampere. And then let's go to the peak of current. At this peak, all of the oxidized species is totally reduced into the reduced species. So this curve is more going down, and then we have a higher slope when compared with the previous cases. Then right now we have 21 microampere, which is larger than the 14 microampere at the point C. That is the maximum value. So what I'd like to emphasize in this slide is that the current is determined by mole flux, and therefore current is determined by concentration gradient. That is the last comment about deriving the equation for mass transfer controlled system. I'd like to add one more consideration to the list of premises for deriving the equation for mass transfer controlled systems. Steady state condition will be assumed for deriving the equation. That is to say, no accumulation of any species is allowed at any point of electrolyte. I have presented this kinetic capability comparison in the first premise. The kinetics of charge transfer is much faster than the kinetics of mass transfer. Then we can say our electrochemical system is controlled by mass transfer. The overall kinetics is limited by and determined by the mass transfer. I'd like to emphasize the word capability in the kinetic capability comparison. VCT is the kinetic capability of charge transfer process without limitation of its computative mass transfer process. The other thing, VMT, which is kinetic capability of mass transfer process without limitation of its computative charge transfer process. Let me give you some number. Right now, you have an electrochemical system with some electrochemical reaction, and the electrochemical reaction has a capability to convert 10 oxidized species to 10 the corresponding reduced species every second. That is the kinetic capability of charge transfer process. Also, in the same electrochemical system, we have the value at 1 oxidized species every second for mass transfer. It means every second only one single oxidized species can approach the surface of electrode. Of course, even if you have a capability for 10 ox per second in the charge transfer process, but you cannot get this value because you have only one oxidized species per second around your electrode of surface. So the overall kinetics is going to 1 ox per second, not the 10 ox per second. So in this situation, your mass transfer rate is 1 ox per second. At the same time, your charge transfer rate is also 1 ox per second, even if this process have a capability of 10 ox per second. This is the steady state condition. You could accept this condition considering no accumulation of any species at any point of electrolyte. Let me imagine some weird situation. You have 10 ox per second for charge transfer and 1 for mass transfer. Then at this point you cannot have any oxidized species. The oxidized species is depleted. Or if you have 1 ox per second for charge transfer and 10 ox per second for mass transfer, the oxidized species would be accumulated at this point. We cannot imagine both cases for these weird situations. So, in many cases, usually we are assuming that the steady state condition. It means the rate of charge transfer is equal to the rate of mass transfer. Of course, in this situation, mass transfer rate is determining the rate of charge transfer. Therefore, do not confuse rate comparison with kinetic capability comparison. Here is the overview about my strategy to obtain the equation about the mass transfer limited system. So let me draw something. Here is the electrode, and as you know, some oxidized species, for example, is approaching the surface of electrode, and then reaction, charge transfer. So in these mass transfer controlled systems, the overall kinetics was determined by the diffusion equation for this process. And then let me think about the situation on the surface of electrode. The surface composition of oxidized species and reduced species is determined by Nernst equation. So let me check each equations. Here is the diffusion equation, current. Okay, so let me start with the mole flux. Mole flux at the surface of electrode is proportional to the concentration gradient at the surface with the diffusivity. Also, current is defined from the surface mole flux. So I per NFA is equal to minus diffusivity with the surface concentration gradient. That is the diffusion equation. You can find the current, and that current is the function of x. Also, you can find the concentration. So diffusion equation is the relationship between current versus concentration. You cannot find any potential term. Let's go to the second equation, which is the Nernst, and electric potential is equal to some standard reduction potential minus log of some concentration term. So Nernst equation can be considered as the relationship between potential and concentration. So by combining those two equations, after removing the concentration term, then we could obtain the relationship between current versus potential. That is our target, and this is related to the voltammetry. Okay, let me start with Nernst equation. Why we are touching the Nernst equation again? Because the Nernst equation is the relationship between potential and concentration, which will be used for deriving the equation for the mass transfer limited system. Let me briefly touch this Nernst equation again, because you have learned about that in the previous chapters. Gibbs free energy is equal to the standard state Gibbs free energy plus some concentration term. Here is the reaction quotient, which is the ratio of the reduced species to oxidized species, or product per reactant. Gibbs free energy can be described by the product of the amount of charge and the electric potential. The amount of charge can be described by minus NF. Here N is the number of electron transfer, the unit of which is mole electron, and F is the Faraday constant, the unit of which is the Coulomb per mole electron. So this is the charge amount. Why should we have the minus sign in front of NF? Because we are thinking about the electron. And the electric potential E is replaced by the electric potential minus equilibrium potential. Also, at the standard state, the same equation is working. By replacing the Gibbs free energy term with the electric potential term, then finally we could obtain the activity version Nernst equation. In this case, you have the standard reduction potential. You are very accustomed to this one. And the other thing is quotient of activity. Of course, when the activities of all species is equal to 1, then the log term is going to 0. So the obtained potential is standard reduction potential. Here is my question. Could you make a solution of one activity of ferric chloride? I have said one activity of ferric chloride. You could. I believe you could. However, you are accustomed to making one molarity solution instead of one activity. It is highly inconvenient to use activity as a measure of the intensive amount of species. Practically, the use of concentration in molarity is more convenient instead of activity. So, I'd like to use the quotient of activity to quotient of concentration. Let me use the relationship between activity and concentration. Activity of species I is just proportional to the concentration of species I. The proportionality is defined as activity coefficient of species I. Therefore, quotient of activity is split into two terms. The first quotient is defined in terms of gamma activity coefficient. The second one is quotient of concentration. That's what I want, quotient of concentration. Then let me put this term into the quotient of activity in the activity version of Nernst equation. Then the log term is split into two terms, and at this point I'd like to define new concept of potential. After merging those first two terms, then we have obtained E0 prime, which is called formal potential instead of the standard reduction potential. So this is the concentration version of Nernst equation. Again, E is equal to formal potential minus RT per NF with log function of quotient of finally concentration. What is the formal potential? Let me put the concentration of all species as 1 molarity into here. Then log term is going to disappear. Then the obtained potential is the formal potential. So the formal potential is the potential at concentrations of all species equal to 1. It's very similar to the standard reduction potential. The standard reduction potential is the potential at the activity of all species is equal to 1. A little bit different, but very similar. So I'd like to use the formal potential instead of the standard reduction potential, because when we use the formal potential, then we could use the concentration term. And also, more easily we could obtain the value of the formal potential, because we could make one molarity of something instead of one activity of something. That's it. So it is the reason why I have derived the concentration version of Nernst equation from the activity version of Nernst equation. Practically, the value of standard reduction potential is used for the formal potential. So you could use the big tables of the standard reduction potential at 25 Celsius degree for the formal potential. However, in this equation, you could use the concentration term instead of activity. This is not really accurate, but approximately we could use the concentration version of Nernst equation with the standard reduction potential for the formal potential. Okay, so then let's go to the diffusion equation. Here's the diffusion equation, and current of species I per NFA is equal to minus diffusivity with the surface concentration gradient. Here is the situation for the electrochemical process where the oxidized species is converted to the reduced species electrode, and the oxidized species is diffused into the surface, and at the surface some portion of oxidized species is converted to the reduced species. So in the bulk region you would have the concentration at the original value of the concentration of oxidized species. Let me say 1 molarity. And then after the reduction on the surface, this 1 molarity concentration is going down to 0.5 concentration. Let me write down here. 1 molarity of oxidized species, ox. And here 0.5 molarity of ox. Let me assume that at the very first time we didn't introduce the reduced species, so 0 more reduced species as the bulk concentration of the reduced species. On the surface of electrode, we have the same concentration of oxidized species, so 0.5 molarity reduced species. And also, let me focus on the surface region. We have some concentration profiles for oxidized species, maybe like that, and then reduced species, probably like this. So here is my semi-empirical assumption. So let me get this part to here, and we don't need to think about the body of electrolyte. We will focus on the surface region because the current is determined by the concentration profile, actually concentration gradient at the surface. I'd like to emphasize this part, at the surface. So let me assume that linear concentration profiles around the surface. So for the oxidized species, let me assume that like that. Of course, at this region, there is a big gap between my assumption and real situation. However, around the surface, there are no difference. Also, another linear concentration profile for the reduced species. This is the core assumption for the semi-empirical approach. Then, we could simplify the diffusion equation from the ODE, ordinary differential equation, into the arithmetic equation. So, the first equation is obtained from the viewpoint of oxidized species, where Iox is the current from the oxidized species standpoint. So Iox per NFA, the same, is equal to concentration difference between the bulk concentration minus the surface concentration. So bulk concentration minus surface concentration. Okay? Then let me merge the diffusivity with the delta x. Delta x means the diffusion length. So di per dx is going to one parameter, which is called mass transfer coefficient of oxidized species. So right now, differential equation is converted to the arithmetic equation, which is simpler than the differential equation, because we have assumed the linear concentration profile. Let me go to the second equation, almost the same. The current of reduced species per NFA is equal to the concentration difference, like in the Iox. Concentration difference with the mass transfer coefficient of reduced species. Here, of course, in the same way, bulk concentration of reduced species minus surface concentration of reduced species. Let me think about the sign. Here the plus and here the minus. I have defined in this situation the direction of current is positive one. I mean, in this situation, cathodic current is defined as the positive current. So oxidized when the oxidized species move toward the surface of electrode, it indicates plus sign. However, reduced species is going away from the surface to the body of electrolyte, then it indicates the direction of the movement is minus. So I'll put the minus sign on the second equation. One more thing. This is the current which is obtained from the oxidized species standpoint, and the second one is the current from the reduced species standpoint. Therefore, even if they have different standpoint, the value and the sign should be the same for both current of oxidized species and current of reduced species. Let me check it. I'd like to assume that the mass transfer coefficient of oxidized species and reduced species is equal to 1. And bulk concentration of oxidized species, I have said 1 molarity minus 0.5 at the surface of electrode. So this is the plus 0.5. At the same time, we could measure the current from the viewpoint of the reduced species. So what is the bulk concentration of reduced species? 0. And 0.5 mole of oxidized species is converted to the 0.5 mole of reduced species. So 0.5 with minus sign. So it is going to plus 0.5. So on the steady state condition, the IOX should be the same as that of the reduced species. Okay, so right now we have two equations for current, and let me think about the very extreme cases. I'd like to apply minus infinity potential into the system. What happens? Then all of the oxidized species could be reduced into reduced species because you have a big negative over potential into the system. So surface concentration of oxidized species is going to 0. Then put this value into the first equation. So I can say current, the L stands for limiting and C stands for cathodic. So limiting current of cathodic process where oxidized species is going to reduce the species. For NFA is going to mass transfer coefficient of oxidized species with bulk concentration of the same species because this is 0. This is the maximum current or limiting current of the cathodic process. Then let's go to the other extreme. I am applying plus infinity potential into the system. Then of course surface reduced species is totally converted to oxidized species. So this value is going to 0. Then the limiting current of anodic process is going to minus the mass transfer coefficient of reduced species with the bulk concentration of reduced species. So I have defined the current, cathodic current as the plus. So this is the plus, and anodic current is minus. This is the minus. Okay, so let me get those current function and the limiting current function from the previous slide. So here the current function for oxidized species, and the other thing is current function for the reduced species. Also I have said on the steady state condition, the ox species for current, I mean the current of ox is equal to current of reduced species equal to the current for this electrochemical process. Anyway, for the oxidized species with the limiting current of cathodic process, then by combining those two equations, then you could obtain this equation. I per I limiting is equal to 1 minus fractional composition of oxidized species, which is defined as the surface concentration per bulk concentration. That is the FOX, fractional composition of oxidized species. And then by reshuffling this equation, fractional composition of oxidized species is equal to 1 minus current versus limiting current, the maximum value of the cathodic process. Or let me write down. And this is the current of limiting for cathodic process minus current I limiting cathodic, and by using this equation, I limiting for cathodic current is going to NFA MOCO star. So by putting this value here, then finally you can obtain this one. I mean, the surface concentration of oxidized species are obtained. From the current of reduced species, also in the same way you could obtain the similar expression about the surface concentration of reduced species. Right now, we know the surface concentration terms, which can be described by current. Then, each time put those surface concentration as a function of current into the Nernst equation. Because you have the potential in the Nernst equation, and inside of log function you can find the surface concentration of reduced species and oxidized species. After putting the description about the surface concentration obtained from the diffusion equation, then you could obtain the relationship between potential and current. That is for the voltammetry. Right now, we have several equations which comes from the diffusion equations. For example, we know the surface concentration of oxidized species and reduced species, which are expressed in terms of the current. Also, the other things are the equations for limiting current. The limiting current is determined by the bulk concentration with mass transfer coefficient. And then we will use those equations and then combine those equations with the Nernst equation. Finally, we obtain the equations for the relationship between potential and current. Before going to the body of derivation, I'd like to expect what kind of shapes for the potential versus current curves. Here are the potential axes from positive values to the negative values. Therefore, in this case, you would have the positive signs for the cathodic process for the current, and minus current indicates the anodic process. I have said we have several equations, and some of those equations is saying about the limiting current for the cathodic limiting current and the anodic limiting current. Let me draw some lines for the limitation. Okay, so the current cannot be developed above the cathodic limiting current. So the cathodic limiting current is obtained from the product of bulk concentration of oxidized species with the mass transfer coefficient of oxidized species. That is the upper limit for the current. How about the lower limit? Another limiting current is here for the anodic process. Of course, it is obtained from the product of bulk concentration of reduced species with the mass transfer coefficient of the corresponding species. Right now, we have two limits for the current. Maybe as the potential is going up, going to the more and more negative directions, the current would approach to the limiting current. Also, when you scan the potential into the positive directions, then your current is approaching the limiting value of the anodic process. Here is one more restrict here. At equilibrium or at equilibrium potential, we should have the current at 0, because at equilibrium the forward reaction should be balanced with the backward reaction. In the other words, at equilibrium potential, your cathodic current should be the same as the anodic current. Therefore, net current should be 0. Again, at equilibrium, you should have the current, or net current should be 0. So your current curve should pass this point. Then you could have some expectation about the potential current relationship. Maybe the current passing through this point at equilibrium potential and approaching the limiting current for the cathodic process or limiting current of anodic process. So the correct answer is this line. This line is passing through the equilibrium point, and also this curve is approaching those two limiting currents. That is our expectation and actually the correct answer for the current versus potential relationship. This is the most generalized case, and where both oxidized species and reduced species are initially present. That is to say, I have introduced 1 millimolarity of Fe3 plus and also at the same time 1 millimolarity of Fe2 plus. Then let me derive the equations for the current potential relationship for these generalized cases. So I have said right now we have 1 millimolarity of Fe3 plus as the oxidized species, and the other thing is 1 millimolarity or sometimes 2 millimolarity, anything is okay, Fe2 plus as the reduced species. That is the situation. Okay, then what we have is those two equations about the surface concentration. Surface concentration of oxidized species and surface concentration for the reduced species. Both of them are expressed by some current with the help of limiting current for the cathodic process and limiting current for the anodic process. And then here is the Nernst equation. In the log term, we have the surface concentration in the Nernst equation. So let me change the Nernst equation to the current here by replacing those surface concentration with those two equations. Then put it there, and put it there. Then finally we could obtain this kind of equation. The first term is still former potential, and the other term is made by the ratio of the oxidized species, the ratio of mass transfer coefficient of oxidized species and reduced species. The third term have the current in each log function. And at this point, I'd like to say about the equilibrium. What is the equilibrium? The current is 0 because at the equilibrium, the cathodic process is balanced with the anodic process. So the net current going to 0. Current is 0 like that. Then after putting the 0 values into I inside of the log term of the third term of the equation, and then E is going to E equilibrium and E0 prime former potential, the same thing, and the other thing is the ratio of limiting current like that. those two terms is merged into those one term. So you can find in the log term the product of the ratio of the mass transfer coefficient and the ratio of the limiting current. This product is going to the ratio of bulk concentration. Please refer to the following equations. Again, the limiting current here, a kind of definition, and the other limiting current is here. And the ratio of the limiting current is the product of the ratio of mass transfer coefficient and the ratio of the bulk concentration. Therefore, the product of mass transfer coefficient with the ratio of limiting current, like this is the same as this one. Then finally, the log term is going to the log of bulk concentration. Again, equilibrium potential is equal to the formal potential minus RT and F log, natural log, of the ratio of bulk concentration, reduced species and oxidized species. This equation is very similar to the original the Nernst equation. Here is the Nernst equation. The difference thing between the Nernst equation and equilibrium potential equation is two things. E is changed into equilibrium potential and surface concentration is changed into the bulk concentration. That is the equilibrium potential. It means that after you have fixed the bulk concentration just before your experiment, then you could expect the equilibrium potential from the concentration you have introduced into your electrolyte. So, for example, in this case, right now you have fixed the concentration of oxidized species and the concentration of reduced species at 1 millimolarity. So let me put those two values into the equation for the equilibrium potential. So 1 millimolarity and 1 millimolarity. So the second term is going to 0. Then equilibrium potential at this situation is observed at the formal potential, which is approximating the standard reduction potential. Okay, right now you have two equations. The first equation here and the second equation about the equilibrium potential. Then let me combine those two things to remove the formal potential. Then the equation is going to potential is equilibrium potential minus RT per NF of log function. And this log function, you can find the current here with the anodic limiting current and cathodic limiting current. This equation can be converted to the other equation like that, which is expressed in terms of the concentration. The numerator is a kind of fractional composition of reduced species, which is the ratio of surface concentration per bulk concentration of reduced species. Also, in the denominator, you could find the fractional composition of oxidized species, which is the ratio of the surface concentration per bulk concentration. That is the final equation. And then, even if you don't need to memorize this equation, but you can memorize it easily in terms of fractional composition. This is very similar to the original Nernst equation, but the first term should be equilibrium potential, and the concentration term is going to the fractional composition, which is the ratio of the surface to bulk instead of just surface concentration. From this equation, you could obtain a very important lesson. At equilibrium, of course, in this case, this concentration term should go to 0. Then, the surface composition is the same as the bulk composition. So, let me say, the surface composition here, Cr star per Co star, should be the same as the surface composition ratio, like Cr at surface per Co at surface. For example, if you have the equimolar concentration for your bulk concentration, then at equilibrium, I'd like to emphasize this point. At equilibrium, you should have the same concentration of Fe3 plus at the surface, which should be equal to the surface concentration of Fe2 plus at equilibrium. If you have used 1 millimolarity of Fe3 plus and 1 millimolarity of Fe2 plus. Let me give you another example. In the other experiment, you have introduced, for example, 1 millimolarity of Fe3 plus and 2.5 millimolarity of Fe2 plus there. Here is the Fe3 plus. Then my question is that what is the surface composition at equilibrium? So you should say the ratio between this one, no, let me say like this way. This one per this one. I mean the surface composition of Fe2 plus per the surface composition of Fe3 plus should be 2.5 at equilibrium potential. That is the very important lesson from this equation. So again, at equilibrium potential, you should have the same ratio of the concentration at the surface, which is equal to the ratio of the bulk concentration. This case A is the most generalized case for the relationship between I, V curve or current potential curve. Let me think about more specialized situation. That is the case B here, and of course I have the some concentration of oxidized species like 1 millimolarity Fe3 plus. However, at this situation, or in this case, I didn't introduce the Fe2 plus to electrolyte. So 0 millimolarity of Fe2 plus are available before your electrochemical analysis. Then in this case, we'll follow the same way presented in the previous slide, but the different thing is that the limiting current of anodic process is going to 0 because Cr star, the bulk concentration of reduced species, is 0. So the surface concentration of reduced species is I minus I of limiting current per some constant is going to just I. For the surface concentration of oxidized species, you will use the same equation. Then here is the Nernst equation. You will put the surface concentration of oxidized species into the denominator of log term. Also, the other thing is surface concentration of reduced species into the numerator of the log term. Then let me reshuffle those equations. Finally, we could obtain this one. So formal potential there, and the second term includes the ratio of the mass transfer coefficient ratio, and the third term would have the current function in the log function. You could expect very easily the shape of the IV curve or current potential curve. You should have the two limitation in terms of the current, and the lower limit is going to 0 because the limiting current of anodic process is going to 0. So it is the 0. And you cannot find the equilibrium potential. Maybe your equilibrium potential could be found at plus infinity volt along the potential axis. So around there at plus infinity for the equilibrium potential. So you could obtain this kind of curves. Okay, let me back to the equation to describe these curves. I'd like to make the third term going to 0. For making this term 0, then the current should be a half of the limiting current. Then this term is going to 2, and 2 minus 1 is going to 1, so log 1 is going to 0. It means let me change the pen to laser point, and at current is equal to half of the limiting current, like that. Then the potential is this one after removing the third term. And let me define this term is the half wave potential. Half wave potential. Half wave means the current value is the half of the limiting current. At that current, we have defined the potential as the half wave potential, or E subscript L per 2. So after following this definition, we could simplify this equation. Then potential is equal to the half wave potential plus RT per NF with log term. And inside the log term, you can find the current. And the current function indicates the ratio of the fractional composition of reduced species per fractional composition of oxidized species, which is the same as that of the previous slide for the more generalized case. However, in this case, we don't have any reduced species like Cr star is equal to 0 or 0 millimolarity of Fe2 plus. So it is difficult to define F reduced or fractional composition of reduced species. So in this case, we have described the fractional composition of reduced species into 1 minus fractional composition of oxidized species. That is the equation for the potential current relationship for this special case B, where we don't have any reduced species in electrolyte. Let's go to another special situation. Case C, insoluble reduced species. For example, we have Fe2 plus in electrolyte. That is the oxidized species. And it is reduced into Fe. Fe is the solid, and this Fe is electrodeposited on the surface of electrode as the solid phase. So the solid phase have the activity at equal to 1. So let's go back to the Nernst equation. The surface concentration of reduced species is fixed at 1 in this special case. Then also we will put the surface concentration of oxidized species as the function of current into the denominator of log function. Then we obtain this kind of equation. Then let me think about those two terms. Formal potential plus RT NF ln CO star. What is that? That is the equilibrium potential. Equilibrium, equilibrium potential. Why? Because here is the Nernst equation. Here's the Nernst equation, and the surface concentration of R, or activity of R, is going to 1, and the other thing is going to CO star. Then you can obtain this equation. So in the case A, as the most generalized case, I have said equilibrium potential is obtained from the Nernst equation when you replace the surface concentration term with the bulk concentration term. So this is the equilibrium potential. Then I'd like to simplify this equation into equilibrium potential plus log function. What is this log function? I mean the term inside the log function. This one is the fractional, the inverse of fractional composition. No. This is the fractional composition of oxidized species. So when you return to minus sign in front of the log term, then I could say the potential is equal to equilibrium potential minus RT per NF log the fractional composition of reduced species per fractional composition of oxidized species. The same shape of the equation which is presented for the most generalized case A. Again, 1 means F, reduced species. Then let me think about the current potential curve. In the most generalized case, you have obtained this kind of the current potential curve like this one, and you have another saturation curve. However, in this special case C with insoluble reduced species, you don't need to think about the other half for the anodic process. So you have obtained this kind of curve, the half of the most general case A. And let me define one more things. E is equal to equilibrium plus something, and then after I sending this equilibrium term into the left side of the reaction, then E minus E equilibrium for the left side of the reaction. This difference is called over potential. Over potential. More specifically, we have said about the mass transfer control system. Everything is determined by concentration term. So this over potential is so-called concentration over potential, which is described by this equation. So in this curve, what is the over potential of concentration? The difference between the equilibrium potential and your applied potential. It means as you have increased the over potential or concentration over potential, you could obtain the higher current, and the current is saturated at very high over potential. Until now, we have derived the semi-empirical relationship between the current and potential. Three cases are presented. Here is the summary table, and the case A, the most generalized case, with some concentration of reduced species and some concentration of oxidized species. Then you would obtain the current potential curve, and the current is saturated at very negative potential or very positive potential. Between them, you could find the equilibrium potential point where the current is zero. If you don't have any reduced species in your electrolyte, you should go to the case B. In this case, the shape of the current potential curve is very similar to the case A. However, the lower limit of this current potential curve should be zero because you don't have any reduced species. It means the lower limit is going to zero. Also, we have discussed about the half-wave potential. Let's go to the case C, and in this case, your reduced species is insoluble. So, you will think about the half part of the most generalized case here, not this one, this one. So erase the other half of the curve, then you could obtain this curve. Also, we have discussed about the concentration of potential for the case C. Let me check the equation. I have said the log term of the potential current curve can be described by the fractional composition of reduced species and fractional composition of oxidized species. Let me think about the same term in the other cases. In case B, this one is F reduced, I mean the fractional composition of reduced. In case C, with insoluble R, the F reduced species or fractional composition of reduced species is equal to 1. So you can understand the log term as the one shape, like log of the ratio of fractional composition, reduced species per oxidized species. You have just derived the relationship, I mean semi-empirical relationship between current and potential. From this slide, I will derive the equation about the semi-empirical relationship between current and time. In this situation, I'd like to apply the very negative overpotential into the system. That is to say, reduction is dominant. The total amount of oxidized species present in electrolyte is totally reduced into reduced species. That is the situation. Then I'd like to give you the curve about the current versus time. This is the chrono-amperometric cases. Also, I'd like to use the same assumption which is used in the previous derivation about the current and potential. So it is the reason why I'm saying the relationship for current versus time is semi-empirical. That assumption is called Nernst diffusion layer treatment. Here is the situation. Electrode and electrolyte. You have some oxidized species. So some value of oxidized species is there as the concentration. Let me say 1 millimolarity of Fe3 plus. Right now I have applied very negative potential into the system. So at the surface the overall the whole amount of oxidized species or Fe3 plus is totally reduced into the reduced species. So the surface concentration of Fe3 plus is 0 millimolarity. And of course you would have some concentration decrease around the surface from the bulk concentration to the surface of electrode. This concentration this decreasing concentration profile is assumed to be linear with the distance from the electrode. I means the linear decrease of the oxidized species from bulk electrolyte into the surface of electrode. That is the linear assumption for the concentration of oxidized species, which was used in the previous example about the current and potential curves. Also, let me define one more thing. Nernst diffusion layer. Only inside the Nernst diffusion layer you could find the concentration gradient. After the diffusion layer, the concentration of electrolyte is always the bulk concentration or CO star. So we could split the electrolyte region into two different regions. The first one is Nernst diffusion layer region. The other thing is bulk region. Actually, this assumption is the same assumption used in the previous derivation of current and potential. One more thing. The thickness of the the thickness of the Nernst diffusion layer from the viewpoint of oxidized species is a kind of time function. So let me say the thickness of the diffusion layer is delta O, and that is the function of the time. And let me sketch what kind of things happen for the thickness. X-axis is the the distance from the electrode, and y-axis is the concentration of oxidized species. At the large value of x, you could find the bulk concentration, CO star. However, around the surface of electrode, you have the smaller value of the oxidized species. In this case, I have applied very negative potential, enough to reduce all of the oxidized species on the surface. So the surface concentration the surface concentration of oxidized species is always 0 after you have applied the potential into the system. Of course, at time equal to 0, you have the bulk concentration even on the surface. So you will follow this line at time equal to 0. However, let me say 1 second later, you have this kind of profile. Okay, at the surface, you should have 0. However, at the surface of the Nernst diffusion layer, you should have the bulk concentration. So this kind of linear slope is obtained within the Nernst diffusion layer. So thickness of this diffusion layer is here, delta of T1. As time goes by, or at the 2 seconds later, um, the front surface of the Nernst diffusion layer is moving toward the bulk electrolyte because more amount of oxidized species is reduced. So you have this kind of line, and then as 3 seconds later, this line. So I mean, as time goes by, the thickness of the Nernst diffusion layer increases. So we'll obtain the function about the thickness of the Nernst diffusion layer first, and then I'll give you the expression of the current as the function of time. The first equation is obtained from the interface. At the interface, current is defined as the mole flux at the surface of electrode. Therefore, that is the diffusion equation at x equal to 0, or the fixed first law. So current per NFA is equal to diffusivity of oxidized species with the concentration gradient at the surface of electrode. And based on the linear assumption for the concentration gradient within the Nernst diffusion layer, this first derivative term is going to the arithmetic term. So delta concentration is going to bulk concentration minus the surface concentration with the thickness of Nernst diffusion layer, delta O. That is the first equation. In the second equation, let me think about moles of oxidized species which is reduced in diffusion layer. Moles of oxidized species reduced in diffusion layer can be obtained by integrating the current per NF with respect to time. So integral of current per NF with dt. That is the amount of oxidized species which is reduced in diffusion layer. So reduction is going to current, then we can describe this amount by the integration of current with something. The other thing, this amount can be calculated by the volume of the diffusion layer with average concentration of reduced species within the diffusion layer, right? Because O is going to R, so by checking the amount of R, then we could quantify the amount of O which is reduced in the diffusion layer. So volume, surface area of the electrode with delta T, the thickness of the diffusion layer. And how can we obtain the average concentration of reduced species? Based on linearity between the concentration and the x value, we could say the average of reduced species is equal to the concentration of reduced species at x equal to delta, I mean the front surface of the diffusion layer, plus the reduced species at the surface of electrode per 2. That is the average because we have the linear concentration profile. Then Each concentration of reduced species could be obtained by bulk minus the oxidized species concentration at that point, at the corresponding point, right? So the first term is that difference at x equal to delta, where the second term is going to the difference at x equal to 0. What is the value about the concentration of oxidized species at x equal to delta? I mean at the front surface of the diffusion layer. That is the bulk concentration. So CO star minus CO star is going to 0. Therefore, the average value of the concentration of reduced species is going to CO star minus surface concentration of oxidized species per 2 here. Okay, that's it. And then I'd like to combine those two equations. From the viewpoint of current per NFA, what is that? That is the flux, mole flux. We obtain this expression from the first equation here. And let me try to find where is the I per NFA in the equation 2. So here's the A. Then let's go to the left side of the equation. And also integral is going to the right side of equation. So this means dt. T or d of all of things. So I per NFA is equal to this term. Those terms are not the function of time, and delta is the function of time. So d delta dt is going there. Then finally we can obtain a very simple ODE, ordinary differential equation. d delta dt is equal to 2 diffusibility of oxidized species per delta t. And what is the initial condition? At time equal to 0, the thickness of diffusion layer is 0. With this governing the ODE and initial condition, you could obtain the solution. I mean, the solution is delta t function, delta function as the function of time. So delta is equal to 2 with root square of diffusibility of oxidized species with time. The most important point of this function is the diffusion layer thickness is proportional to the root square of time. As time goes by, or as time increases, the thickness increases. And the detailed function is the root square of time. And then with this function, I'd like to go to the current description. Current per NFA is this one. So put the delta t function into here. Then we have this one. So finally current is going to this equation. The most important point of this equation is, of course, current is inversely proportional to the time. So it means current would decrease with time, and the detailed function is the root square of time. The inverse function of root square of time. Can you remember the Cottrell equation about the chronoamperometry? At that time, when you apply the constant potential into the system, then your Faradaic reaction current is decreasing with the root square of time. So This semi-empirical relationship is representing the Cottrell equation, even if some parts is a little bit different, because Cottrell equation was obtained from the exact the derivation of ordinary differential equation. However, in this equation obtained from this chapter, we have assumed the linear concentration profile within the Nernst diffusion layer. However, we could obtain the overall behavior of the current versus time. Also, let me check. Here is the diffusivity or the root square of diffusivity, and here is root square of diffusivity. Almost similar to each other, except of you can find the surface concentration in the semi-empirical relationship. We cannot expect the surface concentration value. However, anyway, we what we know from this equation is that the current is inversely proportional to the time, inversely proportional to the root square of time, which is indicated by Cottrell equation.